All right. So, like I said, we're going to go back to limits today, and we're going to look at a way to deal with limits that are indeterminate, specifically limits that are of the form 0 over 0. Right. So we know that when we try to evaluate a limit of a rational function, f of x over g of x, right, or of any, of any quotient of two functions, if the numerator is 0 and the denominator is 0, it's indeterminate. We have to deal with it in some way. And some of the times that was pretty straightforward, factoring or multiplying by the conjugate. But sometimes, like the thing with sine x over x, and we had to do all that extra work with the sandwich theorem, it was kind of a pain. So we have this rule. It's called L'Hopital's rule. Sometimes it's spelled like this. Sometimes it's spelled as L apostrophe hospital. They're both fine. Anyway, it's called L'Hopital's rule. And L'Hopital's rule says that if you have an indeterminate form, 0 over 0 for a limit, that you can take the derivative of the numerator and the derivative of the denominator and evaluate those at this a value. And the result will be the same as the original limit. Okay? Normally I'd go through and prove this, but we're not going to prove it this year. If you want to find a proof of it, you can easily search for the proof of it online. It's not super complicated. But L'Hopital's rule says that if you have 0 over 0, and only if you have 0 over 0, at least for right now, you can take the derivative of the numerator and the derivative of the denominator and evaluate that new function at a, and it'll have the same limit. Does that make sense to everybody?
So when you find the derivative, is most of the time it's a nice function where you just plug it in and it works, or is there more stuff to do after that?
Nope. Usually you take the derivative of the top, take the derivative of the bottom, and it usually will work. Now, not all the time, but usually.
Okay, cool.
And I want to make an important note here that it is not taking the derivative of this whole thing as a function. You are not using the quotient rule. You are taking the derivative of the top, and you are taking the derivative of the bottom. In no way are we taking the derivative of this larger f over g function as a quotient. Okay? We're not actually finding the derivative of f over g. We're just finding the derivative of f, and we're finding the derivative of g, and that ends up having the same limit. Does that make sense? Everybody?
But what does it return?
Say that again.
Once you find the derivative of the numerator and the denominator, what does it return?
If you plug in the a value, it gives you the limit of the original f over g.
Oh, okay.
Right, as long as that limit, the original limit was indeterminate, 0 over 0.
Wait, is there respect to a?
No, you're taking the derivative with respect to x of both of them.
Okay.
Yeah, the f prime of a here is just because I'm plugging in a. Plugging in.
Yeah.
So let's take a look at a couple of them that we probably could have done previously. Hopefully you could do these. The limit as x approaches 2 of x squared minus 4 over x minus 2. So first off, normally we'd plug in our 2, right? And say, oh, this is 0 over 0. And so we could factor the numerator and cancel. And then that wouldn't be difficult in this case, would it?
No.
No, it'd be very easy.
No.
But taking the derivatives of both of those is also very easy. So what we would do is we would write it out, and on the AP test, they want you to say that you use L'Hopital's rule. And you made this the limit as x approaches 2 of what's the derivative of x squared minus 4?
2x.
2x. And what's the derivative of x minus 2?
1.
1. And what is that limit? It is
4.
4.
4.
Yep. And that's it. That's the rule. Had we factored this, right, we would have got x plus 2, x minus 2 in the numerator. The x minus 2's would have canceled, and we would have just had x plus 2. Plug in the 2, and you get 4. Good or no?
So we have to write out L'Hopital's rule every single time? Like,
Every time you use
abbreviate it, or like LH?
No, I used to tell people abbreviated LH, and then College Board sent out this thing that they were no longer going to accept just writing LH. They want you to write out that you use L'Hopital's rule.
That's so stupid.
I 100% agree with you about that. You shouldn't even have to write it at all. I mean, clearly, if you're using it, you know what it is and you know how to use it. So I have a lot of disagreements with the College Board, but unfortunately, we have to follow their rules if you want to succeed on their test. So got to play the game even if it's dumb sometimes. Don't worry, I'll rant about the College Board and some of the things they've decided a bunch more later this year, I promise. Because there's things I hate more than the fact that they make you write out L'Hopital's rule. So.
Can you use this for sine functions like sine x over x?
You can use it for anything as long as it's 0 over 0.
Okay.
Yep. And in fact, we'll have sine x over x in just a couple minutes. So we have this one here. The limit as x approaches 0, root 1 plus x minus 1 over x. Plug in your 0, and what do you get?
0 over 0.
0 over 0. Good. Okay, and so using, and I'm going to be bad. I'm just going to write LH, but don't do that. Write out L'Hopital's rule. This becomes the limit as x approaches 0 of what's the derivative of root 1 plus x?
One half times
1/2 x to the negative 1/2.
Right, 1/2 u, right, which is 1 plus x. So it's 1 over, remember, if this is root u, it's 1 over 2 root u, right? Times the derivative of the 1 plus x, which is just 1. And then the derivative of the minus 1 is
0.
0. And the derivative of the denominator, the derivative of x, is just 1. So when you plug in 0 now, what do you get?
1/2.
1/2. So as long as you can take the derivative fairly easily, you should be able to get this limit very quickly. Probably easier than multiplying by the conjugate and canceling stuff out and simplifying and then plugging into 0. Would you guys agree? Probably easier this way?
Yeah.
Yes.
All right. So what happens if you take the derivative of f and the derivative of g and have f prime of x over g prime of x, but it's still 0 over 0?
Do you take the second derivative?
Right. You should just be able to take the second derivative of each of them and should be able to hopefully get a result then. What do you think will happen if it's still 0 over 0?
Do it again.
Do it again. Just keep doing it until it's no longer 0 over 0, right? So we can do this. We could say we can differentiate as many times as needed. Now, what if it comes out to be 0 over 3 at some point? Then what's your answer?
The limit doesn't exist.
No, if it's 0 over
0.
3, it's 0.
Oh crap, 0, 0. Never mind.
Comes out to be like 3 over 0, then that's when you would say the limit doesn't exist. You can't use L'Hopital's rule if it's like, 3 over 0 or 7 over 0. It has to be 0 over 0. Good or no?
Good.
Okay. So let's take a look at this one. It looks very similar to the one we were using L'Hopital's rule on just a minute ago. The limit as x approaches 0 of root 1 plus x minus 1 minus x over 2 over x squared. Plug in 0. What do you get?
Zero over 0.
You get 0 over 0. So what should we do?
L'Hopital's.
Use L'Hopital's rule.
And you'll write it all the way out. But I'm just going to write LH because I'm lazy and I'm not taking an AP test. The limit as x approaches 0. We know the derivative of root 1 plus x. We just did 1 over 2 root 1 plus x, right? The minus 1 becomes what? 0.
Yeah.
And the minus x over 2 becomes what? Minus
2 minus.
what is x over 2? X over 2 is just 1/2 x, isn't it?
Yeah.
So derivative of 1/2 x is just
1/2.
1/2. And then all over what in the denominator? 2x. So plug in your 0 over 0. What do you get?
0 over 0.
We had 0 over 0. So what should we do? reapply the rule. So in the denominator, we're just going to have a 2, right? And the minus 1/2 is going to go away. So we got to deal with this 1/2 root 1 plus x, or 1/2 of 1 plus x to the negative 1/2 is what that is, right?
Yeah.
So what's the derivative of 1/2 of 1 plus x to the negative 1/2? It should be negative 1/4 times 1 plus x to the negative 3/2 times the derivative of 1 plus x, which is just 1. And now when we plug that in, what do we get? We get negative 1/4 divided by 2. And what is half of negative 1/4? Should be negative 1 over
2.
No,
1/2.
half of 1/4 is an 8.
Whoops, 8.
Yeah. Everybody good with that? Or no?
1 in the first part of the derivative is from the derivative of 1 plus x?
Correct.
Okay.
Yep. Any other questions on that?
So when you were finding the derivative of the numerator in red right there, so you just found the derivative of 1/2 square root 1 plus x, and that's what
Right,
that is right there?
Yeah, I rewrote it as 1/2 of 1 plus x to the negative 1/2 just to make it easier to use the chain rule and the power rule on it. But yeah, I mean, that's what that negative 1/4 1 plus x to the negative 3/2 times the 1 is.
Where'd the 1 come from? I know it doesn't matter, but.
It's the derivative of 1 plus x.
Oh, I see, okay.
So this is 1/2 u to the negative 1/2. So I took the derivative of 1/2 u to the negative 1/2 and then multiplied it by the derivative of u.
I see.
Good or no? Yeah, maybe.
Yeah.
All right. Cool. Let's do, oh, it's sin x over x. Somebody was just asking about that one a minute ago. Remember when we did this one before? Remember how much of a pain it was? We had to draw that unit circle, and we had to draw like 2 different triangles and a sector of the circle and find some areas and do a bunch of algebra and then use the squeeze theorem and find some limits. And remember all that? Wasn't it a pain?
Yeah.
Yeah.
I'll plug in 0. What do you get? 0 over 0? Oh, so using L'Hopital's rule, this ought to equal the limit as x approaches 0 of, oh, what's the derivative of sine? Cosine.
Sine.
And what's the derivative of x? 1. What's the cosine of 0? 1. 1 over 1 is 1. Man, that's so much quicker, so much easier. Isn't that great?
We should have done derivatives first, and then we could have just, because limits were kind of like, once we get to all the rules, you don't need limits for derivatives.
Oh, I
You
mean,
can't start derivatives without limits.
can't do derivatives.
Just
and
jump
no
straight into the
limit.
rules.
I can't do that. You got to teach you where it comes from, even in this like shortened.
No one needs that.
Yeah.
They just need to know what to do.
No, that's the problem with the world today. Actually, don't get me started on the problems of the world today. There's plenty of those. All right, here's another problem of the world today: the indeterminate form of infinity over infinity. Okay? And the indeterminate form infinity over infinity can also have L'Hopital's rule applied to it. So let's think about this. Secant of pi over 2. What's the secant of pi over 2?
Undefined.
Right, it's undefined, right? It's what happens at pi over 2? There's a vertical asymptote there, isn't there? If I just look at secant x, and I'm going to put in here, I'm going to also, I know you can't see the graph, but I'll show you in a second. Here's the graph of secant x, right, in red, and then there's x equals pi over 2. Well, as x approaches pi over 2, right, I think I had a, yeah, as x approaches pi over 2, we're going towards an infinite value. True? You guys agree?
Yeah.
Yeah, so as we're getting close to pi over 2, we're going close towards an infinity value. And what's the bottom function?
1 plus tangent x.
1 plus tangent x. And you should know where tangent has asymptotes, but one of them is at pi over 2, right? And so we're approaching that infinite value also. So we can say that this is infinity over infinity. Okay? And therefore we can use L'Hopital's rule with this also. Okay? So if we're approaching the vertical asymptote of a trig function or of any other function, we can say that that's infinity, right? Because we're not actually getting to pi over 2, so it's not actually undefined, it's just getting exceptionally large. So using L'Hopital's rule, the derivative of secant x.
Secant x tan x.
Secant x, tangent x. That seems like it's going to be a problem, right? Because, well, secant x's limit as we went to pi over 2 is infinity, and so is tangent. So this is just another infinity and another infinity. But we'll see. The 1, what happens to the 1?
Eliminated.
Yeah, it goes away. So then we've got secant squared x. Well, hopefully you can see that we can at least get rid of the secant in the numerator and 1 secant in the denominator, right? Might as well simplify a little.
Yeah.
But tangent x over secant x, well, what does that equal as we go towards pi over 2? Should be, again, infinity over
Infinity over infinity.
That's another infinity over infinity. So what do you think we should do?
Apply.
Go again.
All right, you guys want to go again. So let's do that. So what is that going to become? It's going to become, I'm not writing everything out. It's going to become secant squared over secant x tangent x, right? Well, what's going to happen? I can cancel the secants, and that's going to be secant x over tangent x, isn't it?
Yeah.
Shouldn't you just change tangent
Yeah.
into over cosine?
That seems like a great idea. Let's do that. All right. So you probably note that that's just going to go back and forth between tangent x over secant x and secant x over tangent x, just over and over and over and over again. So let's rewrite it. Rearrange that trig, sine x over cosine x over 1 over cosine x. And then that just becomes the limit as x approaches pi over 2 of what? The cosines cancel. It's just a sine x. And what's the sine of pi over 2?
1.
1. And if we were to look at secant x over 1 plus tangent x, I do that, but I wanted to, but that's fine. Secant x over 1 plus tangent x, as x goes towards pi over 2, sure looks like we are approaching 1, doesn't it? Even though we know that that point doesn't technically exist, right? Because we can't plug in pi over 2, it sure looks like it's approaching 1. Everybody agree with that?
Yeah.
All right. Any issues there? No? Let's do another one. The limit as x approaches infinity of natural log of x over 2 root x. What's the natural log of infinity?
Infinity.
Infinity. And what's the square root of infinity?
Infinity.
Infinity.
Infinity. So we'll use L'Hopital's rule to give us the limit as x approaches infinity. What's the derivative of natural log of x?
1 over x.
And what's the derivative of 2 root x? That should be 2 times the derivative of root x, which is 1 over 2 root x. So that'll just be 1 over root x. And if I plug in infinity, what's 1 over infinity?
Approaching 0 from the.
Approaching 0. And what about down here? Also approaching 0.
Yes.
So this is 0 over 0. So what
Yeah.
should we do with it if it's 0 over 0?
Do it again.
Okay, we could do it again, right? What's another option?
Simplify first.
We could also simplify first. So if you can simplify first, you should. This just becomes the limit as x approaches infinity of, if I flip that root x up, it's root x over x. Well, what's that the same as? 1 over root x. And as x goes to infinity, 1 over root x becomes 1 over infinity, which is
0.
0. Everybody good with that or no?
Yeah.
All right. Let's talk about the order in which things increase. What's the fastest increasing function that you know of?
Exponential.
Exponential function, right? The higher the base, the more quickly it's going to increase. After that, what do you have?
Logarithmic.
Quadratic.
Yeah, not logarithmic. What? Somebody said.
Oh,
Quadratic.
Yeah, well, not just quadratics, but polynomials, right?
Yeah.
Polynomials in descending power. So, x to the 1,000th is going to increase more quickly than x to the third, right? But polynomials in descending order, right? All the way down to linear functions, right? Then what's next?
Logarithms.
Square root.
Root functions, yeah. Root functions and then logarithmic functions. Logarithmic functions are the slowest that still go towards infinity as x approaches infinity. Anybody know what the one type of function that increases more quickly than exponential functions are? Not that we'll deal with them in this class, but just for fun, anybody know?
No.
No. Gosh.
a function with infinity involved in it.
No. Factorial functions. You guys are familiar with factorial?
Isn't that the exclamation point?
Yeah, it's the exclamation point. Like 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And a factorial function actually increases more rapidly than an exponential function does. But we won't deal with those. This is the order in which things increase for what you guys should care about this year. So suppose I gave you something like the limit as x approaches infinity of, and I put one of these on one of your little homework assignments. Suppose it was e to the x over x squared. Well, that's infinity over infinity, but which one increases more rapidly?
E to the x.
Yeah, the e to the x, the numerator does. And so if the numerator is getting bigger faster than the denominator is, what are we going towards?
Infinity.
Infinity. But if I flipped this around, still infinity over infinity, but because the denominator gets larger more quickly than the numerator does, what does it approach?
0.
0. And we could see that easily enough by using L'Hopital's rule, because if I took the derivative of e to the x over x squared, that's e to the x over 2x. And then if we did it again, it'd be e to the x over 2. And now it's just infinity divided by 2, which is infinity, right? But down here, it'd be 2x over e to the x. And then it would become 2 over e to the x, which would be a constant divided by a very large number. 2 over infinity would be 0. You guys see that?
Yeah.
Cool. That's L'Hopital's rule. I'm not going to give you an assignment on L'Hopital's rule yet, because you have that chain rule assignment with like more difficult chain rule problems. But I will give you a L'Hopital's rule assignment. I'll probably post it today, but it won't be due until tomorrow.
Will it be on the quiz on Friday?
It will potentially be on the quiz on. Yeah, everything up until what we've covered today could potentially be on Friday.
Cool.
Yep. All right, that is it.